So if we've got 5 moles of glucose, how many moles of carbon must we have?
30.
We okay with it being 30? Because every time you have one glucose molecule, you have 6 carbon molecules. So if I've got 5 moles of glucose, then that means I've got that number times however many glucose or carbons are inside there. So in this case, I'm going to have 30 mole of carbon, and we'll also have 30 mole of oxygen, and the hydrogen, 60 mole. Okay. What's the total mass of the 5 moles of glucose? All right, so I've got 5 moles C6H12O6. And for every 1 mole of C6H12O6, gram C6H12O6. C6H12O6. So somebody got a molar mass for that? No? Yes, maybe. So 12.011 times 6 plus 1.0095 times 6 plus 15.9994 times, dang it, that's not 6, it's 12. $180, so 180.158. So if I multiply that by 5, I get a total mass of 900 grams. Everybody good with that? That 180 was, where'd I get that from? So that 12.011 from carbon times 6 and 1.00795 times 12 for hydrogen and 15.9994 for times 6 for the oxygen, and then add them up. All right, so we want states. I want the finished balanced chemical equation here. So what happens if I take these two things? So both of these are what kind of compounds? Ionic. They're both salts, right? So if I want two salts to react with each other, what state do they need to be in? They need to be aqueous. They need to be already dissolved. So these guys are aqueous. Okay, so if I want those guys to react with each other, and by aqueous, they must, what does that physically mean has happened to the molecule? They're already broken apart, right? So I already have a magnesium and 2 bromines floating free in water, and I already have a silver and a nitrate floating free in water. So I'm going to dump those 2 containers together, and when I do, the magnesiums and the silvers and the bromides and the nitrates are going to be able to touch each other. And when they have that opportunity to touch each other, does anything happen? Yes, something happens. What happens when the magnesium and silver bump into each other? Why do they not do anything? They're both positive. They never even get a chance to touch each other. Okay. What about the bromines and the nitrates? Same thing, right? But now they're negatively charged. Okay, so what happens if the magnesium runs into the nitrate? It'll like it? Okay. One's positive and one's negative, but what do you mean by they'll like it? I'm not sure how chemical that is. They will not. Why will they not? Nope, it's got nothing to do with the +2, but that's a good guess. We don't have any information about the magnesium. There isn't a magnesium rule, but there is a nitrate rule, and what's the nitrate rule? Rule number 2. It's soluble. So if they bump into each other in water, what are they going to do? They're just going to bump into each other. That's it. Ping, and no actual connection. So what about the silver and the bromide? Is there a bromide rule? There is a bromide rule. What's the bromide rule? That it's soluble. Is there a silver rule? There is a silver rule, and it says it's insoluble. And what about the orientation of those two things? The silver rule comes first, so it supersedes. So of these 4 ions, when they bump into each other, the only thing that's going to cause a reaction to occur is the silver bumping into the nitrate. Sorry, the silver bumping into the bromide. So AgBr. And what state's that going to be? Solid. It's sitting in water, but it's a solid because that silver bromide is insoluble. And then over here, I'm also going to have, I can write down my magnesium nitrate, but it's aqueous. I need to balance this out, so I need to put a 2 right there and a 2 right there. And what's the name of that first thing? Just magnesium bromide, all right. And the second thing? And this? And the last one? Why don't I need any numbers with any of these, like silver 1 or magnesium 2? Nope. They only have one opportunity to have a charge. So silver is only ever +1 and magnesium is only ever +2. So I don't state their charges. So the full ionic equation is me taking everything that's aqueous and separating it out. So I've got a magnesium that's aqueous. I have 2 bromines. It's very important that the 2 is out front. Why? What if I put the 2 down below? Oh, that would say that they're connected. And are they connected? No, because they're both negatively charged, so there's 0 chance they could be connected. So that 2 needs to be out front as a coefficient. Plus 2 silver aqueous and 2 nitrate aqueous. And on the other side, this is still silver bromide as a solid. The only reason that we separated the ones on the left-hand side is because they were all aqueous. That's not the case with the silver bromide. It is a solid, it stays a solid, it's a solid for all 3 of the equations. And then the last one is the magnesium and 2 nitrates. The magnesium is still disassembled because it's aqueous, and so I've got those 2 nitrates out there as well. So now what we have to ask ourselves is, what changed? Ask ourselves what didn't change. So what didn't change from one side of the arrow to the other? This magnesium here is just sitting there as magnesium aqueous +2, and so is that one. What else did not change? 2 nitrates aqueous -1, 2 nitrates aqueous -1. So what do we call those things I've highlighted? Those are the spectator ions. What did they do in the chemical reaction? Nothing. They just watched. So when I go to write my full ionic or my net ionic equation, I write everything I have for a full ionic equation except my spectator, since they didn't do anything. And so, all right.
I've got a question about the ionic equation.
Yeah. The which one? The full ionic?
Yep. For the magnesium and silver.
Yeah.
Because the bromide and the nitrate rules come before it, causes those to be aqueous as single elements in there.
Yeah. Wait, what do you mean by single elements?
Well, just that the magnesium is aqueous and the silver is aqueous.
It's aqueous because magnesium bromide, when it gets put into water, dissolves. There isn't a magnesium rule. There is a bromide rule, but there's no magnesium rule. So what you're looking for to determine if it's going to be aqueous or not is you look at that salt, and in this case it's magnesium bromide, and then I ask, are either of those soluble? Are either of those not soluble? And in this case, I don't know anything about magnesium, but I do know the bromides are soluble. So since when it goes into water, the bromide lets go, the magnesium automatically is on its own. Is that, I feel like I'm not answering your question.
Yeah, just trying to figure out how, like, you know, because if just magnesium and without bromide, it'd be solid.
Yeah, because it's elemental magnesium with all of its electrons. But this
as long as
magnesium,
with the bromide, then it has to be aqueous if it's together.
if the magnesium is in a compound, it's not magnesium metal anymore. It's magnesium ion. It's lost those 2 electrons that it has for valence. And so whatever it's combined with in a salt, its solubility is dictated by that anion. And that same thing over here with the nitrates and the silvers. I look at that and there's 2 rules there. There's a silver rule that says I'm insoluble, but there's a nitrate rule that says I'm soluble. And the nitrate rule is higher on the list, so it supersedes the silver's rule, and so it is soluble. Okay. Write out a balanced chemical equation for propane gas and oxygen. We're going to combust this. So it's C3H8 gas plus O2 gas, making carbon dioxide, gas, and water. All right, gas, doesn't really matter. Okay, so what are we going to do to balance the carbons? Put a 3 over on this side on the carbon dioxide. So now my carbons are balanced. What do you want to balance next? I don't want to balance the oxygen next. I don't want to balance the oxygen next because how many different substances are the oxygens in? 3 different substances, right? So what that'll do for me is if I make a change in one thing, there's a possibility that I could have changed the amount in another thing. So I'm going to do the hydrogens next because how many species are the hydrogen found in? Just 2, 1 on each side. So if I throw a 4 up here, I balance my carbons and my hydrogens now, and now I can balance my oxygens. Because on the right-hand side, I can see that there are 10 total oxygens, and on the left, there's only one thing that needs to be changed, the O2. And so if I throw a 5 in front of that, then it's all balanced. So I'm starting off with 25 grams of propane. That's the mass that I'm going to start with. And I want to convert that into how many grams of water I'm going to make if I burn this whole 25 grams of propane. What is that? It's when we ask this, when I'm asking you this question, I'm making an assumption. What's the assumption? Okay, but we definitely know that already because we already wrote down the chemical equation. Say again?
Do you have propane actually there?
No, I already said we have 25 grams of it there. But what haven't I talked about being there?
Any of
I haven't said anything about the oxygen, right? So with a question like this that doesn't mention any of the other reactants, the question is saying you have to have enough of that reactant. If I had 1 gram of oxygen, it doesn't matter how much propane I have. I can't make the correct amount of water. So when you get a question like this, the assumption is you have plenty of the other reactants to use all 25 grams up. Okay? So in this case, we're saying I've got 25 grams of propane and as much O2 as I need to burn all of the 25 grams of propane. That's the assumption that's being made. So I got 25 grams of propane, but I don't really care about anything's mass. What do I need to do first? I need to count it, right? So I do that by turning it into moles. I'm turning it into a number of propane molecules. So for every 1 mole of C3H8, I have some number of grams of C3H8. It's like 44. 0.096. Okay, so what does this step do for me? Okay, it cancels out the grams, but what else does it do? it just counted my number of propanes. It turned my mass of propane into a number of propanes, because moles is actually a count, like dozens. So now I will, if I did the math for this, I would know how many moles of propane I have, and that would tell me how many actual propane molecules I have, which I have to know my number of propane molecules, right? Because up here, that's one propane molecule makes 4 water molecules. And that's going to be the next step, is give me that ratio. For every 1 mole of C3H8, it's 4 moles of water. So now what did I just do? I just counted what I'm looking for, right? So if I told you I had 10 bicycles, can you tell me how many pedals are there? We know for every bike there's 2 pedals, right? So there's 20 pedals there. That's what we just did here. So in this first step, what I did is I knew the total mass of all the bicycles that I had, and all the bicycles are exactly the same bicycle. And then I used however much each bicycle's mass is per bicycle. And so that told me how many bicycles I had. And then this next step is for every 1 bicycle, there's 2 pedals. And then I calculate the mass of each of the pedals, or for every 1 pedal, and this is the total mass. And so that'll tell you how much the pedal mass is. So we're doing this on, obviously, the atomic scale. So it's not as easy to think about. And then for every 1 mole of water molecules, it's 18 point, anybody have that? And answer to this, anybody? Oh yeah. And I'm gonna just go 40.0 because it's, I know there's a bunch of decimal places here that are less than 5. And I only have 2 sig figs for this, right? I started with the 25. So then my answer has 2 sig figs, so it'll be 40 with a decimal place telling me that that 0 in the 40 is significant. So why did I have to go back to mass? Once I've counted it, how come that's not good enough? Okay, that's a really good answer, but is there another answer? Why I asked for grams?
Because it started out.
No. I can't count them, right? If I stopped with this spot right here at this 4 and just said how many moles of water I had, that's telling you how many moles of water molecules there are. And it's a really huge number. Could you go into the lab and count? No, you can't count. So we always start with grams and end with grams because that's the only way that we can pseudo count the molecules. Otherwise, we'll be dead before we can actually count out our 40 grams of water. Okay.